Okay, in this final lesson we'll have a look at the kinetic model of an ideal gas, and we'll go over the assumptions of the kinetic model, and then we'll have a little look at what the kinetic model of an ideal gas looks like in a simulation. So our objectives here are to state the assumptions of the kinetic model of an ideal gas, to state that temperature is a measure of the average random kinetic energy of the molecules of an ideal gas, and to explain the macroscopic behavior of an ideal gas in terms of a molecular model. Now, the assumptions of the kinetic model of an ideal gas. Firstly, the gas is a pure substance, so it contains only one type of particle. That ensures that all the particles have the same mass. The number of particles in the sample is large, so that statistical methods are valid. These particles are also in constant random motion. So this is a two-dimensional representation of what that would look like. We have all the particles moving constantly and randomly. We also assume that there are no forces between the particles except during the collisions. So the particles move in straight lines. This is not something like when we were looking at for example, changes of state. We needed to assume that there were forces between the particles to explain the concept of latent heat. So when we're dealing with an ideal gas, we're going to do away with the idea that there's a force between the particles that's attracting them, and instead we're going to assume that they're just floating around like little billiard balls that only exert a force on each other when they collide. We also assume that the particles are very small compared to the average separation of the particles. So they're bouncing around, and essentially each particle is confined to a small point in space, and the amount of free space between the particles is very large compared to the amount of space that's actually occupied by the particles themselves. The particles, when they do collide, make perfectly elastic collisions with each other and with the walls of the container. This ensures that the gas doesn't lose kinetic energy through the collisions. So we need to make this assumption because basically what we've done before when we've said that collisions are inelastic is that the energy is lost as heat. But in this case what we're trying to explain is heat, so we can't really say that in the collisions the particles lose energy to heat. And so we assume that all of the collisions are perfectly elastic. And finally, all of the particles obey Newton's laws of motion. That's Newton's first, second, and third law of motion. Now, using these assumptions, we can build quite a powerful model of how a gas behaves macroscopically in terms of how we are assuming the individual particles are moving. And the equation that comes out of this we'll study in the higher level topic on thermodynamics. But the equation that does come out of this is very good at predicting behaviors of gases within certain temperature ranges. So we'll have a look now at a simulation to make sense of how an ideal gas behaves. The first thing that we want to explain is that temperature is a measure of the average random kinetic energy of the molecules of an ideal gas. So what I'll do is I'll just pump in some molecules here. So we now have a bunch of particles in an ideal gas within this box. Now, one assumption that's not really being met here is that the number of particles is very large, because we have a countable number of particles here, whereas the ideal gas model assumes that we have so many that the laws of statistics are true with very small errors. Anyway, it's still a fair representation, and it'll give us a good sense of what's going on. All of the particles have different speeds at different times, so we can't really define what the kinetic energy of each particle is. However, we can talk about the average kinetic energy, because during the collisions are all elastic, and so the average kinetic energy shouldn't change. So the average kinetic energy in this system remains constant, and that's the term that is related to temperature. And what we can do is just click on measurement tools here and add species information. And what we can see here is that we have 112 molecules, but more interestingly, their average speed is close to 430 meters per second. It fluctuates a bit, and again, that's because we don't have enough particles for the statistics to be quite right. But the average speed, of course, is related to the kinetic energy by E equals half mv squared. And so you can see that the average speed relates to the average kinetic energy. All of these particles are identical, and so only the speed of the particles can change the energy. And indeed, if we add heat so that the temperature rises here, we can see that as the temperature rises, the average speed rises, therefore the average kinetic energy rises. And so in fact, another thing that we can do, just to make this doubly clear, is that this of course shows that as the temperature rises, the kinetic energy, the average kinetic energy of the particles rises. But we can show that it's not just related to the average speed of the particles, because if we use instead a lighter particle, so if we want to get up to this 457 Kelvin, with the heavier particle, the average speed at 457 is about 520 meters per second. If we use lighter particles and we increase the temperature to about 457, the average speed is much greater. It's 1,380-ish, somewhere around 1,300, 1,400 meters per second. However, because they're lighter, their kinetic energy is still the same. So their average kinetic energy is still the same. So at 457 Kelvin, the average kinetic energy of particles is always the same. So if it's a light particle, they'll be traveling very quickly, which means that their average kinetic energy is high. If it's a heavier particle, then they'll be traveling more slowly, which means that however, because of their mass, they'll have the same amount of kinetic energy if the temperature is the same, on average. Okay, so that's the concept of temperature. What we'll now do is just have a look at the some of the relationships in an ideal gas. Alright, so as we've already mentioned, a gas will exert a pressure on every surface of its container. As the gas molecules collide with the walls of the container, they'll exert a force on the walls. The force is proportional to the change in momentum of the particles. Thus, the pressure depends on the number of collisions that are happening with the walls per second, and the change in momentum of each molecule that collides. And that depends on both the speed and the mass of the molecule. So firstly, the first thing that we can change here is the number of molecules, n. So if I pump in a bunch of molecules here, and we keep the volume and temperature constant, and we have a look at the pressure here. So we currently have a pressure of 0.45 atmospheres roughly. If I double the amount of particles without changing the temperature or the volume, we can see that the pressure increases. In fact, it pretty much doubles. And so if we increase the number of molecules and we keep the volume and the temperature fixed, then the pressure will increase. In fact, the two are proportional. The reason for this is that we now have more particles confined to the same space. In fact, we have twice as many particles confined to the same space, which means that we'll have twice as many collisions with the walls, and the particles on average have the same amount of kinetic energy, as it says here, so the change in momentum in each collision will be the same. Twice the number of collisions with the same amount of force will result in twice the pressure. Okay. The next concept is that as we increase V, the volume, the pressure will decrease. And we can see this. I'll just shrink this volume down a little bit. I'll put in some molecules. What we'll do is we'll just keep the temperature constant now. And as I increase so basically what the average kinetic energy of the particles is going to remain the same throughout here. And we're going to have a look at what happens to the pressure as I increase the volume. So we can see that the pressure is dropping as the volume gets larger. And we can make sense of this because the particles are now much further apart. There will be fewer collisions, and the particles on average have further to travel to get from one collision with a wall to another collision with a wall, which means that the frequency of collisions has gotten smaller. So even though each collision exerts the same amount of force, because we have fewer collisions, there's a smaller force, there's a smaller pressure on each wall. And this results in the relationship between volume and pressure at a constant temperature. If we increase the volume, the pressure will decrease. So pressure and volume are inversely proportional if temperature is maintained, if temperature is kept constant. Thirdly, if we keep the volume constant and we increase the temperature, what we're doing is we're increasing the average kinetic energy of the particles. And so that means that in each collision there is a greater change in momentum of the particle, which means that each collision of a particle with a wall exerts a larger force on the wall, which means that even though, and because they're traveling more quickly, they will also collide with the walls more frequently. So increasing the temperature increases both the frequency of collisions and the force of each collision. And so as we increase the temperature, we see an increase in the pressure when the volume is kept constant. Alright, finally, if we keep the pressure constant and we increase the temperature, so let's just reset to shrink this down. Let's keep the pressure constant. Let's pump in some gas particles and just let it reach a sort of stable equilibrium here. So this guy's got to adjust the volume until the pressure is roughly constant. So it looks like he's just about figured it out. Okay, so now if we increase the temperature and keeping the pressure constant throughout, what we can see is that as the temperature increases, the volume has to increase in order to keep the pressure constant. The reason for this is that when each particle has more kinetic energy, it'll collide, as we said previously, it'll collide more frequently with the walls, and each collision will exert a larger force on the wall, so the pressure would increase. However, if we increase the volume by a corresponding amount, then we can sort of compensate for the fact that the particles are moving much more quickly, because in an increased volume the particles also have to travel further in order to collide once again with another wall. And so in order to keep pressure constant, as we increase the temperature, the volume will have to increase. And this is something that we're going to look at in detail in the higher level topic, because this is really the key to getting a gas to do work, to converting heat to work, which is kind of the key to the steam engine and to any system that we use to produce energy using heat. So that's the basics of relating the macroscopic concepts of pressure, volume, and temperature to what's going on with the individual molecules in an ideal gas. Now, to describe real gases, the physics or the kind of mechanics of each particle has to be made a lot more advanced, but the principles are the same. We use the fact that each individual particle must behave in a predictable way, and then we average out the behavior of all the particles using statistics, and that allows us to figure out how this whole collection of particles will behave macroscopically.